Vectors. Not our favorite character from a Despicable Me movie. But, well, for short, to put it mildly, this is going to make our diagrams a lot more exact. It's kind of the easiest way to think about it. It is still very trig related. We're still talking about triangles as far as everything is going. So don't think that we're straying from that, because we're not. But it is just an application that is fairly specific. So I am not going to have us do a couple of finding the distance between each of these 2 points. I'm sure we can do some Pythagorean theorem or distance formula. I'm sure we're used to that. There are some answers there if you'd like to get them in simplest radical form, which we should also know. We'll move past that. Vectors, what we're talking about today. Vectors are visual representations of forces applied to objects. They're represented basically like arrows. You can think of it as a line segment, sort of. I mean, kind of, we named them the same way. This is vector AB. And this is a visual representation of what we could possibly apply to a force in some way. Apply to an object, like a force, acceleration, velocity. A vector is quantity like so. And the 2 things we care about is that it has a very specific direction and a very specific length, which we call a magnitude. Now, you've probably been sitting here going, all right, this seems like it's going to be super complicated. And I'm here to tell you, really not. This is the way I think about it. Now, again, this is just engineer brain going. We just kind of like draw diagrams a lot of times, just trying to figure stuff up, kind of haphazardly draw stuff. I don't know. Here, let me do my old school physics. We have an object, and there's a box, okay? And then we have a couple, like here, that's a force that's being pulled, and then there's gravity, and then, there's this normal force, and let's put some friction on it, whatever. And I kind of just randomly draw all those arrows there, and they're supposed to represent certain forces. Now, technically those arrows, those are vectors. They're forces applied to my object, but I kind of just haphazardly drew them. What we're just saying right now, for lack of a better term, is that whenever you draw those arrows, you should kind of be specific about them. You really should. Vectors have a very specific length and a very specific direction. That means if I'm pulling with a certain force that is equivalent to, 4 newtons, I should probably draw it 4 boxes long. If I'm pulling it at an angle, I shouldn't just kind of arbitrarily pick an angle. I should actually go at the angle it's actually going at. I just want to be specific with this. Now, worth noting, we name vectors. You can either name it just like we see this is vector V. It's got a V. It's got the little vector symbol above it, kind of like we'd do a ray or segment line. And we name them by their initial and terminal point. In that order, by the way, that's kind of a big deal. This is vector AB, which tells me it's the vector going that way. That matters. Direction matters. Why? Well, because angles for vectors are always measured from the positive x-axis, and then they go around counterclockwise. That means that for this vector right here, if I'm going to calculate its direction, that is to say its angle measure, I would draw the horizontal x-axis. Hopefully a little bit better than this. And I would find this angle measure right there. And let me see if I can draw theta with this. This will be tough. Hey, theta. I would find that angle measure from the horizontal x-axis, and I measure it upward. If I switched it, if I said the vector was BA, now that changes things. BA now implies the vector is going that direction, which means, in essence, at B, if this was my new initial point, I have to find the angle that goes all the way around. So it's more than 180 degrees, actually, going downward. Now, yes, there are ways to specify direction based on, like if you're on a map, north, south, east, west, you can give information that way to kind of adjust stuff. But shy of that, you're always measuring from the horizontal x-axis counterclockwise. So we need to be specific with naming. And then, mathematically speaking, vectors are typically represented in what we call component form. They're like angled parentheses, kind of like an ordered pair. And they're thought of in the same way. Much like how an ordered pair goes x-coordinate then y-coordinate, for a vector, my vector over here is CD, it goes 2 units in the x direction and 3 units in the y direction. So its component form is going to be 2x, 3, y. The only thing we care about, of course, is direction matters. So that's the positive x-axis. Or let me refrain. That's the positive x direction. Location doesn't matter. Vectors are direction and magnitude, length. Where we put them, you'll notice there's no coordinate plane here. Doesn't really matter. You can move vectors wherever you want to make things a lot easier. So that, where it's at, but it's going 2 units in the positive x direction and 3 units up positive y direction. That does matter also, because again, this is vector CD. If we were doing vector DC going that way, we're going both in the negative x direction and the negative y direction. So my component form would have been -2, -3. Direction matters. There is also, by the way, just so you know, there is another way to write this. It's called IJ form. It's really the same stuff, but if my component form is 2, 3, so my component form is 2, 3, like that, IJ form is written as 2I plus 3J. I know, hard, right? It's like it's on an IJ axis, I suppose. You can think of it that way. Used in different forms, different applications, but represented the exact same way. So if you see IJ, it's just x and y, as far as how far it goes in the x, how far it goes in the y. That's it. So, here's a vector. Vector HG. I want to write it in component form, and we'll do IJ form, I suppose, just as a lark. We see the direction. Okay, that's the negative x direction. So I'm going a certain distance in the negative x, but then it's going up. So my component form, I consider, okay. Now, fortunately, we're on a grid here, so we can just count boxes. Eventually, other things will come into play, like I'll mention in a moment on my end. I'm going to go, it looks like, all right, so here's where my initial point is. I'm going to go 1, 2, it looks like 3 units in the negative x direction. And then it looks like I'm going 1, 2, 3, it looks like 5 units in the positive y direction. So -3, 5. Or, IJ form, -3 plus 5j. Just so you know, this sign right here, in between IJ form, is based on the y component. This is positive, so we're positive here. If this was negative, we'd be minus. I know, again, really tough, right? Anyway. Here. I could also give you endpoints. So, I mean, you can do any number of things. Maybe draw it. That's one thing you could do. But I tend to just subtract, distance formula. Sorry, not distance formula. The distance between any 2 points. Like the distance between any 2 points is just subtract where they're at. I mean, yeah, -8, 1, and 2, 7. Here, not accurate at all drawing. -8, 1. 2, -7. So it goes like that. Ish. Very accurate, right? Yeah. Take your x's, subtract them. Take your y's, subtract them. That's how you find the distance between any 2 points anyway. Difference. Delta. So, 2 minus -8, 10. -7 minus 1, -8. which makes sense because positive x direction and then down. So yeah, 10, negative 8. Not hard. Let's try one. Easy one. I'd like the vector u in component form. Pause the video. See what you got. Alright, both are negative because negative x direction and negative y direction. I count. Well, easiest way. 1, 2, 3. 3 units over. And it looks like it's 1, 2, 3, 4 units down. Ooh, that's easy. Negative 3, negative 4. Or negative 3i minus 4j. You know, this would be a good time to point out, we're also going to be paying attention to that direction thing. Let's consider that. So I have a vector that went over, here's my initial, over 1, 2, 3, down 1, 2, 3, 4. Okay, there's my vector. Draw some components. Three units, we'll just say absolute value because of the actual distance covered. We know it's negative 3 in the negative x direction and 4 in the negative y. Okay, fine. Direction matters, and without any other orientation, all we know is that we have to consider direction from the positive x-axis, which is over here. So that means I need to calculate what this angle is. Now, is that super hard to do? I mean, maybe if you're trying to think of the big, massive, over 180 degree angle it is. But I would never do that. What we should do are basic trigonometric calculations, which we've been working on for a while now. What I would do, this is me, I mean, you have other options, of course. But what I would do is I would note, okay, it's going to be 180 degrees, plus, here, let's call this theta. So why don't I just solve for theta and add that to 180? Probably the easiest thing to do. It's a tangent calculation. Opposite is 4, adjacent is 3. Tangent theta is 4/3. Theta is equal to inverse tangent 4/3. I don't know. Calculator. I have 4 calculators on my phone, emulators, and I can't find one of them. Got it. 4 enter 3 divide inverse tangent. I'm getting 53 and change. Three decimal places, because obviously that's what they use in the AP exam. So that's kind of what we're considering here. Like, that's what we have to do. We're considering angles, how we write stuff. Oh, and that's theta, by the way. That is not the direction. I would have to do 180 plus 53 and change. So keep all these things in mind. Anyway, here one more. There's 2 points. I give you initial and terminal. Why don't you tell me what the component and ij form of is of this vector? Pause the video and let me know. All right. You could have drawn it. -1, 1, 6, 2. Or maybe just subtract. 6 minus -1 is 7. 2 minus 1 is 1. 7, 1. You can do it in your head. It's not that hard. Or 7i plus 1j. But you wouldn't write 1. You don't do that. Plus j. Anyway. Okay. So, with that being said, the other thing, aside from doing direction, is we're going to find the magnitude. But the magnitude is just the length. Like, literally, that's all it is. It's not anything more complicated than that. Don't think it is. And you know how to find the length of diagonal distances. It's just going to be a right triangle. These are Pythagorean theorem problems. That's all they are. If you know a vector that you're going to analyze, the component form tells you the legs of the right triangle. So I have this vector. That's -1, 5 in component form. That tells me one leg is 1 unit long. Now, yes, it's 1 unit in the negative x direction. Do we care about that? No. Then we're going to add 5. Then we're going to have 5 in the other direction. That's another leg. Now, if you want to be really technical, you can put this vector at the origin and draw negative 1, 5 and do a bunch of distance formula stuff. Or you can just do 1 squared plus 5 squared equals the magnitude squared. It's the same thing. I don't, like, in essence, like, let's be real here. We don't care about this. We don't care about this. We don't care about 0. Maybe we'll care about the 1 part. Well, we do care about the 1. We can make it negative 2 because we're going to square it, right? We don't care about squaring. So negative 1 squared plus 5 squared equals my answer squared. That's all we do. That's it. Really very easy. Oops. Here we go. So here. Okay. 3, 1. You have a diagonal distance. So you might draw it. It goes that way. 3 squared, negative 3 squared plus 1 squared equals your magnitude squared. It's root 10. 9 plus 1. 3.2-ish. Magnitude is just Pythagorean theorem. Direction is just inverse trig. We've been doing this for goodness knows how long. Not something we have to worry about. Shouldn't be, at least. Old stuff. I mean, I'm not going to lie. There are other old things you have to consider. Like, hopefully, like, Pythagorean theorem is something you're going to have to consider. You should know that. Slopes. Because there's rise over run here. Things like that. You'll have to consider. These are things I expect of you. We're in this class by now. Be alert. So that's magnitude. So far, direction, inverse trig, magnitude. Pythagorean theorem. Up until now, this nothing should be that earth-shattering. Now, we will discuss a few other things as we start moving along with this. It's not always the easiest, most straightforward stuff. Well, it kind of is. You just kind of have to know what we're looking for. Like a unit vector. A unit vector is exactly what it sounds like. It's a vector that's 1 unit long. So, and every vector has a corresponding unit vector. So if I have a vector that goes this way, and it is a certain magnitude, cool. My unit vector is that exact same direction, but only 1 unit long. So what do I have to do? What does that entail? Let's say, all right, example. Let's say I have a vector that is 6, 8 in component form. Cool. We should already know the magnitude. Right? Things I expect you to know. 6, 8 legs of a triangle. That's a 6, 8, 10 right triangle. Pythagorean triples. We should know that. But I will be nice. Let's see. Why don't we draw this? All right, let's go here. All right. So I'm just going to draw my vector. 6, 8, correct? Yes, 6, 8. So we'll start it here. We'll go over 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Oh, here, let me have a straight edge for a reason. You know what? Let's just use this as a good time. Hey, this is one of the reasons I do everything on graph paper. Vectors are a very good example of why you should do things like precisely, neatly. Like 6, 8. It's helpful when you do these right. Anyway. So here's how unit vectors work. This is my normal vector that has components of 6 and 8. 6, 8. Cool. By the way, all right. We know the magnitude is 10 because we know our Pythagorean triples. We definitely don't have to tell ourselves that 6 squared plus 8 squared equals the hypotenuse squared. So 36 plus 64 equals the hypotenuse squared. 100 equals the hypotenuse squared. We can take the absolute value of both sides and we can take the square root. H equals 10. And we only care about the positive version because it's an actual distance. There's a lot of other things. Steps I'm skipping for the purpose of this. Anyway. Cool. That's my vector. It is 10 units long. I want the corresponding unit vector that is only 1 unit long. So what do? Well, I'm just going to take this magnitude and divide it by 10, obviously. That 10 divided by 10 is 1. That will make my entire unit vector divided by 10. Oh, sorry, divided by 10 to get it down to 1. 10 divided by 10 is 1. Well, in essence, what you're doing is creating a similar triangle. If that triangle is 1, I've taken 10, divided it down to get 1. Divided it by 10 to get 1. So I should divide all of these legs also by 10 to get the corresponding components of the unit vector. So here's the thing you do. All you realize that, oh, so this must be the leg divided by 10, and this must be the other leg divided by 10. All you do to find the components of your unit vector is, well, you just take the components and divide it by the magnitude. I mean, simplify, of course. 4/5, 3/5. But, like, take the components and divide by your magnitude. So, my unit vector, we'll say UV, is going to be 3/5, 4/5. So that's my unit vector. Again, same ideas. That's a similar triangle thing. I just took every side, divided by 10, because 10 was the magnitude. If the magnitude was 20, I divide everything by 20. If the magnitude was 4, divide everything by 4. If the magnitude was 1, you wouldn't do anything because it's already a unit vector. That's it. Just divide by the magnitude. You have your components, divide by the magnitude. All right. So that's probably the last small thing we're doing. Now let's get into the stuff that kind of matters. Resultants. Now, what this is saying is that what's going to happen is, well, remember my free body diagram? That a whole bunch of forces applied to them? You could apply a bunch of forces. You can have a bunch of vectors. But in the end, I want to know where I'm ultimately going to be at after all of this is applied. Where do I finish up at? That's what a resultant vector does. It represents the sum of, well, 2 or more vectors. Now, when it's 2, it's very simple. When it's 2, there are 2 very easy ways to find resultants. We call a head-to-tail method, where if you have 2 vectors, you just draw one, and then you add the second one by placing it directly at the head of the previous one. You put the tails there, and then where they connect, where you start to where you end, that's your resultant vector. And that's what you analyze. You could also do it with the parallelogram method, but this really seems like it's redundant because it's just head-to-tail method 2 different ways. You start at a point, and regardless of which one you start at, you add the second one. Anyway. But you can do this with 2 or many different vectors. Here's what the end goal always is. Let's say, I don't know, I'm going this direction. I'm starting here. And then I'm going this direction. So, I don't know, a single geese, good verbiage. A goose is flying this direction. And then there's a strong wind that's pushing him this way, or it this way. And then all of a sudden it decides to go backwards. I don't know. This is a terrible analogy. Whatever. Okay, fine. Whatever. I could do this forever. And there's a lot of things that go into this. If I break all of these vectors down, though, I could do that. There's three on my page right now. Here, let me break them down. I'm going to count and be specific. 1, 2, 3, 4, 5. And it goes up 2. Okay. Now this one, over 2. And it looks like it's up 3. Ooh, this one goes backwards. Backwards 2, 3, up 2. Here's what a resultant is going to have you do. Here's what you're ever going to do if you have a bunch of forces that are represented with vectors. What you're always going to end up being asked is, all right, you started here. You ended there. What's the net result? What's that? When you're done, your net result almost always is going to be like a diagonal vector. And that is what you need to analyze. That, your net result, I'm going to ask you, what's its direction and magnitude? Because that's all we care about vectors. What's its direction, angle measurement, with respect to the positive x-axis? And how long is it? Magnitude. Now, if I initially had just given you the red arrow and just said, tell me direction and magnitude, you don't have a problem. Because you probably just put it into a right triangle. You probably count the boxes. Looks like it's 4. And up 7. You could probably just do that, no problem. And you're doing Pythagorean theorem with 4 squared plus 7 squared equals your magnitude squared. And you're going to find your direction by doing an inverse tangent of 7 over 4. But everyone wants to get really crazy when you apply multiple things. What do I do? There's so many words. Here's what you do. Go back to the components of each individual part that made the final resultant. Negative 3, 2. 2, 3. 5, 2. Add. All you're going to do is add up all of your x horizontal components and all of your y vertical components. 2 plus 3 plus 2, that's 7. 3 and 2 is 7, minus 3 is 4. Oh my goodness. All you're going to do, add up all of the x components, horizontals, add up all of the y components, verticals, and that is your right triangle problem that we've been doing forever. That's it. Now, it's easy for me when I do this, and the vector is really simple. It's not going to be easy. Whoa. When you see, what am I doing? When you see, sorry, this is what I'm saying. Add up all the x's, add up all the y's. But when you see this, everyone's like, no! It doesn't help when the shoulder's still there, right? It'd been more like if I should like throw myself to the floor. Anyway. An airplane is flying at a constant speed of 400 miles an hour at a bearing of north 70 degrees east. A 60 mile an hour wind is blowing due north. What are the plane's actual speed and direction? Round speed to the nearest tenth and direction to the nearest degree. Whoa. Hey. It's okay. It's fine. Medic! Someone passed out. This problem is just that problem, except there's only 2 things. 2. what this is a really long-winded way of saying you've got a vector of 400 going that way and 60 going that way. How about those? There's two vectors. That's it. Now, sure, maybe we didn't know what north 70 degrees east meant. Okay, we'll work on that. But if I gave you the diagram, you'd be like, oh, I can find y, I can find x. Those are just trigonometric calculations. I have my angle. 400 in essence is the hypotenuse, because that's what the magnitude is. Remember hypotenuse? Just finding the length. It's hypotenuse of a right triangle. You know the angle, so it's sine and cosine calculations. X is going to be 20 cosine 400. Y is going to be 20 sine 400. I know that because I've been doing this for way too long. There, sine and cosine. There you go. Then we go back to the diagram. You probably weren't paying attention. Sine of 20 is opposite over hypotenuse. Sine of 20 is y over 400. Cosine of 20 is x over hypotenuse. Cosine of 20 is x over 400. So you're going to solve for x and y. I have broken down this red vector, this diagonal vector, into its components. Yeah, they're a little messy. Yeah, 400 cosine 20 and 400 sine 20 aren't the nicest things. But you know what? It's just a component form with Ucky decimals. Ucky. Sorry, it's my son. Yeah, not very fun. But it's not like... It's the same idea as this. Same thing. And then, the only other vector is just one that goes straight up. So literally, you're just going to add nothing in the 0, and you're going to add 60. And much like I did, not that, and much like we did here, where you just add all the horizontal components and add all the vertical components to get what turn out to be your horizontal leg and vertical leg of the vector that you're trying to finally analyze. So's that. It's ugly. It sucks. 379 and change. Almost 200. But that's just horizontal leg, vertical leg. Pythagorean theorem. Inverse tangent. Opposite over adjacent. Opposite over adjacent, sorry. Opposite over adjacent. It's the same thing. Nothing changes. But everyone wants to make it change. Everyone wants to make it hard. Because words. Don't let it. Not that bad. And this resultant idea is probably the thing that will trip people up the most. But if we realize that when I said the speed, that's just the magnitude. So many things are just the magnitude. Pretty much if we're talking about like something representing, it's like a rate, it's a magnitude. And then I'll just give you a direction. Theta. You can do these. It's not that bad. You just want to make it that bad because everything has to be complicated because it's math and trigonometry and oh my gosh. No. You're okay with this. You can do Pythagorean theorem. You can do some trig. Just add vectors by adding the respective components. Now we're going to do more of this. This is just the first day of all of this. Wait till class. We'll practice a lot, I promise. That's where we're at. Vectors are not that bad. That guy's kind of bad. If you have any questions, don't hesitate to reach out. Be good, y'all.